Well, so it is now 7 p.m. So let's start. Okay, so hi, this is Shavik. This is a 12th session of Points of Topology in PTL NOC course. Um, and This is the 12th session. So tomorrow the session will be tomorrow Saturday. The session will be from 5 to 6, and that will be the last session of this whole course. So if you have any doubt or any questions to ask, you can ask me or you can drop an email. I shall get back to you as much as possible. Okay. So before starting, let me know. It's who's this? It's Mustaq. Okay. So before starting, Mustaq, let me know whether I'm audible and is the screen visible to you or not. Am I audible?
Audible.
Okay. Okay. And can you please confirm whether is my voice coming to be low or is my voice is okay or not? Can you please confirm whether my voice is low or is it fine? Okay. And can you please confirm whether my screen is visible to you or not? Well, so 1 minute. Let's check everything okay fine or not. Well, okay, that's good. Okay. So today let's start with some problem solving. So first problem is as 1 minute. So first problem is as follows. 1 minute. 1 minute. 1 minute, Mustaq. It seems there's some issue with the one application. 1 minute. Kindly hold a minute. Though there is an issue to one or simply the software itself. It's not coming. Why? So kindly hold a minute, please. 1 minute. Okay. Yes, now it is working. Fine. Okay, Mustaq. So now can you please confirm whether the screen is visible to you?
Visible.
Okay, thank you, Mustaq. Okay, so today let's now start with some problems. So 1 minute. So let me. Okay. So first problem is the following. Okay. So let me maintain the order of the question. So this is eighth number question. So okay, so this is question number eight. Now the theorem is as follows. I mean the question is as follows. A topological space is called a Noetherian. A topological space is called a Noetherian. It's Noetherian if for every family Fn of closed subsets of X satisfying Fn plus 1 subset of Fn for all n. There exists M in N such that f of m plus k is equal to fm for all k belongs to n. Okay, so this is the definition of identity. So basically, as you have seen in the possibly you have seen the same definition in the geometry algebra. Here also the same thing. A topological space will be said to be Noetherian if for every family Fn of closed subsets of X satisfying Fn plus 1 subset Fn for all, there exists M belongs to there is a natural number M such that after the certain is M all the sets are equal. Okay, that is called a Noetherian element. Now, question is the following. The question is show that every Noetherian space is compact. How to show? So here you need to show that every Noetherian space is compact. How to show that? Show that every Noetherian space is compact. So how to do? So I mean, okay. So of course it is not quite direct. It's quite tricky. So you need to. So okay. So let me write the solution because it's the argument is quite tricky. Okay. So let me write the solution. And one more thing, if you have any doubt, you can ask me and you can ask your question, okay? Because this session is the most of our lives problem solving session, so that expected that you will ask questions, okay? Or if you have any problem with particular concept from this session or from the previous session, you can also ask me, okay? Okay. So the answers. So let now set so let X be Noetherian. Now let if possible X be non-compact. A possible exponent compact. Okay, and let C be an open cover for X having no finite subcover. Now consider. So we are going with the contradictory argument. I mean, so we are with the contradiction method. Okay. So suppose 1 minute. Having no finite subcover. Okay, 1 minute. Okay. So uh, so let's see we are not so let's see be an open cover for X having no finite subcover. Okay. Now consider um C1 belongs to C and set D1 is equal to C1. Now having defined Dn is equal to C1 union order union Cn, we first choose Cn plus 1 belongs to C with the property that Cn plus 1 intersection x minus Dn non-empty. And we are define Dn plus 1 is equal to C1 order union Cn plus 1. Then we see that then we see that x minus D1 contains x minus D2 contains x minus D3 dot dot dot. This is strictly decreasing chain of closed sources of X, which is which contradicts the Noetherianness, which contradicts the Noetherianness for X. So what how the argument goes? So the argument follows by the contradictor method. Suppose X is non-compact, okay, and C be an open cover of X having no finite subcode, okay. We are taking a C1 below. Say that we are taking open cover. We are defining D1 to be C1, and then after defining D1, we are defining inductively Dn is equal to union of Cn, where first to Cn plus 1 minus C is the property that Cn intersection x minus J non-empty. Okay. Now we are defining Dn plus 1 is equal to C1 union Cn plus 1. Then we see that x minus D1 contains properly x minus d2 contains properly x minus d3. This is strictly decreasing chain of closed subsets of X. Okay, and this contradicts the Noetherianness of X. So this tells that the Noetherian this tell 1 minute. Hmm. This tells that the Noetherian topological space um, hmm, states that Noetherian top this tells that space is not Noetherian. Okay, so there's a contradiction. So this tells that um, our given space um, is compact. Okay, so this is the argument. Now, now, second question. Second question is that prove that a topological X space X is connected if and only if every continuous function f from X to plus minus 1 is a constant function. So we need to show that every topological space X is connected if and only every continuous function f from x to plus minus 1 is a constant function. How to do that? Hmm, How to do that? So, well, so firstly, what does the by we mean by compact connectedness? Connected means the only space is both open and closed. and x is x at 5. Okay, this is what by we by connected space. So how to do it? It is quite easy, but let me write the solution. Okay. Firstly, observe that since continuous image, since x connected, so of course fx connected. Okay. So, but of course, but double down plus or minus one is not, this set is not connected. So if x equal to one, or if x equal to minus one, but this is one direction. Conversely, let f from x to plus minus one be constant for all if for all if contains function x to plus minus one. Okay, and let x is not connected. Is simple. X can be written as C union D or C D, both open and closed in X, and C intersection D is empty. Okay. Now define f from x to plus minus 1 as send c goes to 1 for all c belongs to c, and d goes to minus 1 for all d belongs to d. Okay. So this implies what? This implies f. So, but so f is continuous by what? By Green lemma. So f is a function from x to plus minus 1, but not constant. A contradiction. Correct. So this tells that the function f. This tells that this tells what? This tells that if the function f from x2 was constant for all continuous function a to 1, then this space has to be connected. So how the argument? Let me repeat the argument here. So since x is connected, so fx connected, but plus minus was not connected. So fx equal to 1 or fx equal to minus 1. Conversely, f is equal to x comma plus minus 1 make constant for all f belongs to, for all f belongs to c to x to plus. So this states that x is not connected. So these implies what? These implies x equal to c union d, where c and d are both open and closed. C intersection empty. Now we are defining a map f from x to plus minus 1 as follows. We are sending c, we are sending c goes to 1 and d goes to minus 1. So f is continuous by Green lemma. So this implies what? This implies there exists a continuous function f to plus minus 1, which is not a constant function at all. So this contradicts the assumption on this physics itself. So this tells that our assumption is wrong, that is f is continuous. Okay, so this is the argument. I hope till now everything is clear. Let me know if you have any doubt, any question till now, you can ask. Let me know. If you have any doubt, any question, you can ask or let me know. Okay. Now let's go to the next question. It is a prove or disprove type of question. Sorry. Prove but disprove. Okay. Suppose if an be a sequence of connected subset of a topological space X such that n plus 1 subset n for all n, then intersection an is connected. So an is a sequence of continuous function on Z such that in subset of an, then you need to show that intersection is connected. Okay, so let me 1 minute mistake. So let me need to show in here n is connected. Okay, so how to do? Think about it. You take a few minutes. So what is the question you have? Some an is a sequence of connected subset topology space X and such that an plus 1 subset an for all n. You need to show that the union of n is connected. How to do? So this well. So 1 minute. So so this can be done. I mean, well, so mm, okay. So think about it. So firstly, so let me tell you how to tackle this problem. First, you understand. I mean, okay. In order to show something connected, what are the tools we have? I mean, of course, we have the definition, but of course, by using definition, this type of problem is not possible to solve for. So, what are the technique or process we have available till now? So, we have the fact that if we, I mean, continuous image of a connected space connected, that is one possibility. Another possible way is to method contradiction. That suppose the space is disconnected, suppose space is not connected, and by using that, we somehow can try to show that a given space that we could somehow come up with some kind of counter example. Okay, or suppose just in the previous exercise we have seen a criteria that if a space is a connected if and all every continuous map from x to plus minus 1 is singleton, sorry, constant. So these are the ways we can use. Okay, now of course, now tell me, so I mean of course, so we can, so so okay, let me give the hint here first. Then you should try for a few minutes. If not, you are able to get, then um I am here to write the solution. Okay. So hint, um, method of contradiction, method of contradiction. That is, let union n is disconnected. That is, this union an can be written as C union D, where C and D are kloppen in union an, and C intersection D is empty. Sorry, it should be empty. Now, somehow try to show or somehow try to come up with some kind of contradiction, okay? Or uh, else we can, okay, first think about it, okay? So think for a few minutes. I shall get back to you. In the meantime, let me search some other questions paper too. Well, so okay, so mm, well, so now let's proceed by using this contradiction. Okay, so Ruru, so now, so okay, so look, uh, so since n subset of a and is equal to d, okay, okay. Now, since n connected, so either an subset of C or an subset of D, of course. So without loss of generality, assume an subset of C, okay, for some and not for some and not, okay. Now, if an not plus one subset of D, this implies a not intersection an not plus one empty. But that is not possible since an not plus one subset of an not. So of course, so yeah. So this implies so it tells a n subset of C for all n greater than or equal to n. And if an minus 1 belongs to D, these also is an not minus 1 intersection an not empty. So that is also not possible. So this implies an subset of D for all n less than n naught. So combining get a n subset of C for all n. This implies union a n is a subset of C. Okay, and since these things forms a separation, so here of course C and D non-empty. So this tells what? This tells D is equal to empty, which is a contradiction, correct? So, so in that we can prove this. So well, so let me one minute. So let me repeat the argument here. So, hmm, so since so we shall go with by method of contradiction. So suppose union of n is disconnected. Okay. So suppose union of n are disconnected. So union of n can be written as C union D or n connected. Okay. Now since n is connected, so either n subset of C or n subset of D. So without loss of zero, we can assume that n subset of C. Now if n not plus one subset of D, that would imply that n not intersection n one minute. Yeah. हाँ yes yes I no no actually आप नहीं थे इसलिए oh अच्छा sorry okay yeah yeah hmm. हाँ So the thing is that okay. So this is
Can you repeat this question once again?
okay. Sure, Mustaq. Sure. Hmm. Okay. Okay. So let me go from the starting. So the question is that if n is a sequence of connected subsets of topological space X such that n plus one subset an for all n, then union of n is connected. Okay. Now, okay. So this is what I need to show. Okay. So now look, this problem can be solved by several methods. Okay. So one method is a method of contradiction. So here we're assuming that union of n is disconnected. Okay. So then union of n is equal to C union D, where C and D are Clopen sets in union of n. Okay. And C and D are non-empty, and of course the intersection is empty. Okay. Now, now, so now since now n subset of union of n which is equal to C union D. So now since n is connected and since n subset of C union D, so n will either entirely contain the C or entirely lie in T. Otherwise n will be disconnected, right? So without loss of generality, we can assume that an is subset of C. Okay. Now from this for some n naught. Okay, so from this fact that n naught subset of C, we are going to show that n is subset of C for all n. Okay, so how to do? So assume that the next term, namely n naught plus 1, this is subset of D. So this implies what? This n naught intersection n plus 1, this is empty coming. Correct? Empty coming. But that is not possible since given that phi n naught plus 1 subset n, the intersection cannot be empty. Okay. So this implies what? This implies that n subset for all greater than n naught. And now we are going to show that those indices which are less than n naught, those also lies inside C. How to do? So suppose if n naught minus 1 subset D, this n naught minus 1 intersection n naught is going to be empty. So this implies n subset of C for all n less than n naught. So combining that n subset of C for all n, and this is union of n subset of C, and this is D is equal to empty. So that is a contradiction. Okay. So do you understand, Mustaq? Do you understand, Mustaq?
Yes, yes.
Okay.
So,
Okay. Okay. Thank you, Mustaq. Now, let me now. Okay. So this is one conventional way of solving this problem. So now let me describe a way of solving this term problem by other method, which is quite easy, I guess. Okay. So alternative solution. Okay. So initially we have seen a in the previous question we have seen that if a topological space is connected, if and only every continuous function f from x to plus minus 1 is constant. Okay, that is what we are going to use here. Okay, so let f from unit a n to plus minus 1 be a continuous function. Correct? Okay, be a continuous function. Okay, now we need to show that to show what to show f is constant. Okay, how to prove that? To show f is constant. Okay, how to prove that? This can improve in the following way. I mean, look. So now f restricted to an from an to plus minus 1. Okay, for each restriction. Okay, so this implies f of a. So this implies f of n is constant as n connected. Let f of an is equal to plus 1. Okay, now we are going to show f of some n naught n is equal to plus, sorry, is equal to plus 1 for all n. Okay, how to prove this? How to prove it? How to prove a claim? So let f of a n naught plus 1 is equal to minus 1. Okay, so this implies what? This implies that f of a n naught intersection f of a n naught plus 1 is equal to empty. This implies what? This implies f inverse f of a naught intersection f inverse f of naught plus 1 intersection empty. And now a n naught subset of f inverse f of a naught and a n naught plus 1 subset of f inverse f of a naught plus 1. So this thing gives a n naught intersection a n naught plus 1, which is subset of f inverse f of a n naught intersection f inverse f of naught plus 1. This is empty, okay? So that is, this tells the a naught intersection plus empty, and that is the contradiction. So this implies what? This implies f of a n, f of a n is equal to plus 1 for all n greater than belongs to n. And similarly, we can show that, and see the similar argument. Similarly, f of a n is equal to plus for all n greater than n. Not similarly, f of a n is equal to plus 1 for all n less than n. Okay, so this solves the, this solves the problem. Okay, so now let me again repeat the argument here. Sorry. So in this argument, what we are actually using that let f is a function from unit a n to plus minus 1 by a constant function. Okay. Hmm. And we're going to show that f is constant. Okay. So for in order to show that, we need to use the connectedness of the ans. Okay. Now since f is continuous function union n, so if we restrict f to each of a n, so that make constant. So choose a n naught, and suppose f of a n naught is equal to plus 1. From this, we are going to show that f of um, or actually the more interesting trick is the follows. Actually, this implies, so this is what? So this implies we can use some interesting factor, right? So f of a n naught minus 1 subset of f, sorry, a n naught plus 1 subset of a n naught, which is equal to plus 1. So this implies what? This implies f of a n naught plus 1. So plus, and this is one possibility. This implies f of a n is equal to plus 1 for all n greater than n naught. Okay, so this is one possible, one technique one can use. Okay, but essentially both arguments are same. Okay, so this is the thing. So in this way, you can show that the consecutive terms intersection is non and each connected union is also connected. Okay, so this is the argument. So let me know, do you have any question or doubt, or we can move to the next question now. Let me know, do you have any question or doubt, or we can move to the next question now. Okay, so now let's go to the next question, which is namely that question is as follows. Let x and y be connected topological space, and if A is a non-negative subset of x, B is a non-negative subset of y, then show that product topology x cross y minus B is connected. So if x y connected to polar space, and if A is a non-negative subset of x and B is a non-negative subset of y, then we need to show the product under product of polar x cross y minus A cross B is connected. Okay. So how to show this? So well, this, I mean, so basically let me draw a diagram here. So here we have x and here we have y. Okay. And this is our x, this is one, this is our y, okay. This is our A, this is our A, and suppose these are B. So this is our A cross B, okay. Of course, the rest of the portion is connected, okay. Now think about it. I shall get back to think about it and let me know how to attack this problem. I shall get back to you after a few minutes, okay. Please think about it. Well, so so okay. So can you give me some suggestion, or can you give me some idea how to solve this problem? I mean, well, it's not very 1 minute. Well, it's not difficult, okay? Just you need to go along with the definitions. Anybody have any idea? Well, so I mean, okay, so I understand that from picture it seems quite clear, but of course we need to prove it. So let's make an attempt to prove this problem, okay? So 1 minute. Well, so let's try to prove it, okay? So okay, this proof is not quite small, it's quite big proof, okay? So so please try to follow the proof line by line. Okay. So what we will show, we shall show that given any PQ, pair of points of x cross y minus a cross b, P and Q lies in the same connected component of x cross y minus a cross b. And to see this, let p is equal to x1 comma y and q is equal to x2 comma y2 belongs to x cross y minus a cross b. And then, without loss of generality, assume x1 does not belong to a. Okay, without loss of generality, assume x1 does not belong to a. Now, there are two cases. First is case 1. Let x2 does not belong to a. Okay, now let y3 belongs to y minus b. And now since y is homeomorphic with x1 singleton y, so the point x1 comma y1 and x1 comma y3 are in the same component of x cross y minus a cross b. Okay. Now since okay, so after writing the argument, I will show you, after at least from pictorial point of view, how that argument means. Okay. Now since x cross y, so since x is homeomorphic to x cross y3, so x1 y3 and x2 y3 are in the same connected component of x cross y minus a cross b. Now again, y is homeomorphic with x2 cross y. So this what? This tells that x2 cross y. I mean, this tells that x2 comma y3 and x2 comma y2 are in same connected component. Okay, correct. Same kind of component of x cross y minus a cross y. Okay, so this is one way. So this is one way of the solution. Now let me give the other. Let me give for the case two. Case two. let y2 does not belongs to me. Further, how the argument goes. Now, since y is homeomorphic with x1 cross y, so we get that x1 y1 and x1 y2 are in the same connected component of x cross y minus a cross y. Now, since x is homeomorphic to x cross y2, this implies that x1 y2 and x2 y2 are in same component component of of x cross y minus a cross b. This tells what? This tells p and q belong to the same connected component of x cross y minus a cross b. Okay. So how this algorithm goes? So that is so okay. So basically, what we're doing is the following. So here we have some x and we have some y. Okay, and here we have AB. Okay, we're choosing a point x1, y1. Okay, outside this. So suppose this is x1, this is y1. Okay. So now what are we doing? So this is the line. So this is what this is. X cross y1. And this line is what? This line is x1 cross y. Okay. Now, if we take the union of such lines, this line, and if we take union of these lines, this whole union will get what? This whole union will get x cross y minus a cross b. So this is the thing, okay? And so this is the thing that we wrote in the full argument. Okay? So this thing can be write in a more elegant way. So below I'm writing the alternative way of writing the below. I'm going to represent an alternative way of writing the solution. Okay, alternative way. Okay, how this works? This works as follows. Hmm. This alternative way goes as follows. Pick x naught belongs to x minus and y naught belongs to y minus. Put c is equal to x naught cross y, x cross y naught. Okay, and observe that for any x belongs to S or respectively to Y, singular x cross Y, respectively singular Y is to Y or respectively X, and hence is connected. And therefore C subset of X cross Y minus A cross B is connected. So this is argument. Now, given any x comma y does not belong to A cross B, it's enough to produce a connected Z of x cross y minus cross B such that x comma y belongs to Z at J intersection C. Now why this? So this is basically saying that if we have any bigger topological space, and if we want to show that it's connected, it's enough to show that for any chosen 2 points, there is a connected subspace current with that 2 point, then space will be connected. Why this? Okay, think about it. Now suppose x comma y does not belongs to A cross B. It is enough to okay now so okay so wait a minute. Now suppose x does not belongs to A, then put z equal to x cross y and check z intersection C x comma y not. Okay. Otherwise, y does not belong to me. And then take z to be x cross singular y and check that z intersection C is equal to x naught comma y naught. Okay. So this is the argument. So let me go through the argument. So in the picture showing in the screen, so basically what is 1 bit? So basically, what is our target to do? We have some A and B. So in the picture, you show there is a vertical lines and there's a horizontal lines. Okay. So choose a point x comma y outside A cross B. Okay. So then consider the vertical lines x cross y. One consider the horizontal lines singleton x cross y. Okay. And if you take the union, that union will be nothing but x cross A minus A cross B. So that will be connected. So this is the whole argument that is written in the proof. Okay, there is nothing much extra I have written. I mean, so whatever the visual relation we have, the same thing is written, okay, in the more elegant way. Okay, so that is the thing. So till now, let me know that is it one, one minute, please. Okay, so till now, let me know. Do you have any doubt, any question, especially particularly this last problem? Any doubt? If you have, you can ask me. This problem is quite tricky as per I know. Okay, Avinash. Okay. Thank you, Avinash, for a response. Okay, so it's so then of course I guess. Okay, so now let's go to the next problem. 1 minute. Okay. So now let's go to the next problem here. Okay. So the next problem is as follows. Okay. The next problem is as follows. So the statement is as follows. Let X be a topological space. Then show that X is connected if and only if for every proper subset A of X. We have del of A is non-empty. So how to put this? So what we need to do? We need to suppose this topological space. We need to show that X is connected for every proper subset A of X. We have boundary of A is non-empty. How to do? So well, this is quite tricky. So the argument goes as follows. So this is the method by method of is a method of contradiction. We are doing the by method of by contradiction method. Okay. So let there exist a subset of X such that boundary of M to empty. Okay. Now then A is equal to A minus boundary of M with interior of it, and A is equal to A closure minus boundary of A which is A closure. These both things are fine. This both things implies A is both open and closed in X. So this implies A is empty. Okay. So but that is not possible. So boundary of A has to be empty. This is first, and the second, and conversely, if X is not connected, so this implies there exists a proper subset A in X which is both open and closed, and hence del of U is empty. So how the argument goes? So what we need to show? So look. Firstly, look at the statement itself. So it gives another criterion of a topological space to be connected. So X is connected if and only for every proper subset of X, we have boundary of A is non-empty. Okay. So firstly, we shall go by the method of contradiction. So let there exist a subset of X of the boundary of A is empty, okay, and A is equal to A minus boundary of A is A interior, and A is equal to A closure minus boundary of A that is A closure. But this implies what? This implies A is both open and closed in X, and this implies A is equal to empty. But that is not possible because by a choice A is a non-empty set. Okay? Conversely, if X is not connected, so there is a proper subset A of X which is both open and closed, and which tells that boundary of A is non-empty, boundary of A is empty. Okay, so this is the argument. Okay, now let me find the next question. Okay, till now, do you have any doubt on the question you asked me? Now let's get to the next problem. Okay, I hope till now everything is clear. If you're in a doubt, you're gonna stop me and ask me. Hmm. Now let's go to the next problem. Consider R with usual topology and let AB belongs to R such that A less than. Now question is that classify the following intervals in R up to homeomorphism. Consider R with usual topology and AB belongs to R such that A less than A. Question classify the following intervals in R up to homeomorphism. Okay, so what are the given intervals? One is open interval AB, and is close interval AB, and the close interval A open interval B, and then minus infinity B, minus A infinity closed B, A infinity, third bracket infinity, minus, minus. So basically, what we need to group those together which are homeomorphic to each other. Okay. So in this type of problem, you need to use whatever you know real compact is connectedness so that you can apply the property of the fact the continuous function inverse image. Continuous function image is compact and connected. Okay. So now firstly, okay. So this is open interval AB. Okay. This is open and this is closed. Okay. So now, of course, the open interval AB is not homeomorphic to closed interval AB due to compactness. Due to compactness, correct? This is one. Okay. And now, suppose open interval AB is homeomorphic to closed interval AB, closed open B. Now, if we remove, okay. So look, this is closed A, this is open. If we remove one point, so we have one point removed from here, but then this will be disconnected. This will be disconnected. It will still connect. So open interval AB is not homeomorphic to open A, closed open B. Okay. Similarly, open interval AB is not homeomorphic to open A, closed B. Okay. And similarly, open interval AB is not homeomorphic to minus VD closed B and not homeomorphic to closed A open 3D. Okay. Of course, open interval AB is homeomorphic to Homeowner to what? Homeowner minus infinity minus b minus b minus b. This is homeowner with open A infinity, open A infinity. This is homeowner with minus infinity minus infinity. Okay, so this is the thing. So groups will as follows: open AB minus b minus b, A infinity minus infinity minus b. Okay, now closed A open B. This is another part minus infinity um, closed B, closed A open infinity. This is another. Okay, then closed AB. So 3, 4, 5, 6, 4, 5, 6, 7, 8, 12, 8 is there. So this is the argument. Okay. And here how these are homeomorphic. These are homeomorphic due to basically stretching. How? So if we have open AB, so we can stretch this up to infinity in that way. Okay. So this is the way of solving these problems. So basically in this type problem, what we need to do, you somehow need to use connect as a compactor in order to show that these homeomorphic. The most usual technique is to somehow um, if you omit a point that you might if you omit a point you might notice that one is still homomorphic, one is still connected or compared but other is not, so that is one possibility to show that two things are not homomorphic. Okay? So this is a process, so I mean, okay, so this is the thing. So now okay, so till now, do you have any doubt or any question? Please let me know. Okay, so now let's go to the next question. Well, so now, the similar kind of question um, can be given as follows. Um, hmm. So this is a parabola, right? This is a parabola, right? Okay. So this is a hyperbola, correct? And this is a circle. This is hyperbola. Question is, are they homeomorphic to each other? Are these homeomorphic to each other?
No, they are not. No.
Okay, well, why?
Because you see, circle is rounded and the bola is not rounded.
Well, that's a very good observation. So your argument basically involves the compactness thing, right? So can you please tell the same
So we
argument with the
can say that
connected?
compound. It is
And
circle is connected,
yeah,
hyperbola is not.
correct, correct, very
Same
good, very good,
compound hyperbola is not.
correct, 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 very good, awesome, nice. So well, so as per Mustak told, so one can directly use compactness, one can directly use compactness or connectedness. Connectedness after removing one point. Okay, so this is the thing. So now, okay, now tell me another next interesting question. Um, are the S1 and S2 homeomorphic? That is usual circle and sphere. Are they homeomorphic or not? Now think about circle and sphere. Are these two homeomorphic or not? So look, in this case, circle, of course, the circle sphere both are compact, both are connected. So now, how to prove that? Well, look, I mean, obviously, look. So let me give some different type of flavor for this question. Okay. So look, suppose I mean, so at least from diagram, it is quite. I mean, obviously, circle and sphere cannot be homeomorphic because homeomorphic means they are kind of same. One can be obtained from other by some kind of stretching, pushing, all that thing. Okay. But of
So
course, yeah. Tell me.
while is two, they
Hmm.
are not homeomorphic.
Yes. Why?
But if you cut a point, take a point from S1, and if
Yes.
also you take a point from S2.
Yes.
Yes, from you will take a point from S2, it will be connected. But if you take a
Yes.
point from S1, it will not be connected.
No, no. If we remove a point from S1, that is still be connected, right? Correct?
Yeah.
If we remove a point from S1, that will still be connected, right? So whatever you told, just apply for removing 2 points. So if we remove 2 points,
2 point.
it will look like this, which is disconnected. And if we remove these 2 points, then this will be connected. So in that way, we can show this, okay? But so this is one way. But of course, so your argument is correct. We need to remove 2 points. But of course, uh, but this proof depends on heavy visualization, right? So but in this way we cannot prove that. So then I mean, so of course, how to prove that Sn and Sn plus 1 are not homeomorphic? So of course Sn and Sn minus 1 means they are, I mean, in Sn plus 1, Sn is the basically meridian circle. How to show that a homeomorphic? Because here we don't have any kind of visualization, right? For for that thing, there is a sophisticated tool. For that thing, there is a sophisticated tool in topology known as algebraic topology. Okay. So look, I mean, this problem Sn plus 1 is not possible directly by removing something. Okay. Or it might be possible, but it's very complicated because there is no kind of visualization. So directly it is not easily easy to be proved. So in that, so for this type of situation, there is a special branch of topology known as algebraic topology. Okay, in algebraic topology, there is some new concepts like homotopy, homology, cohomology. Okay, and there is a fact like suppose two spaces are homomorphic, then their corresponding homotopy. By the way, homotopy, homology, cohomology, all are these groups. Okay, so there is a fact like if two spaces are homomorphic, then they are homotopy groups, homology groups, cohomology, all are isomorphic. Okay, and for sphere case, they are for Sn and Sn plus 1, their homology, cohomology groups are not isomorphic. That's why they are not homomorphic. Okay. One minute. One minute. Okay. Hmm. So, okay. So basically, okay. So what I was saying is the following. So, since so, huh, so okay. So there is a special branch of topology known as algebraic topology, and in that branch, there is some concept like homotopy, homology, cohomology, and it's a fact that if two spaces are homeomorphic, then their corresponding homology, cohomology, or homotopy groups are isomorphic. But for Sn, Sn plus one, this is not the case. That's why for Sn, Sn minus one, all are they are not homeomorphic. Okay, so this is one possible way of solving this type of problems. Okay, so now, um, sorry. Okay, so now, okay, similarly, show that it is which mark. Okay, it's just a question. I did not put the marks here. Show that, show that R and R2 are not homeomorphic. Show that R and R2 are not homeomorphic. How to do? Hmm. So how to do that? Okay, so As for the sphere case, if we somehow use the fact that suppose this R and this R2, and if we remove one point here, this then becomes disconnected. But if we remove one point from here, then becomes connected. Sorry, if you remove also one from here, then also it becomes connected. So this is one possible way to show that. Um, so this is one so this is basically one possible way to show that um, what so this is one possible so this tells that R minus singleton point and R2 minus singleton point not homeomorphic. So this tells so this tells hmm, so this tells that R and R2 are not homeomorphic. Okay, so that is the argument. So, but okay, so this argument can be solved by using by removing some points. Okay, but but hmm, hmm, one minute. Hmm. So this tells us but now how to but now of course but now how to but now how to show Rn and Rm is not homeo for all m not equal to m. So this is so this problem how to show. Hmm. So how to show this? So okay, so if you try to do this by using the removing points or lines on a plane technique, then I'm sorry to say this technique will not work for higher dimensional cases because in higher dimensional cases, since there is no visualization, so proving this argument by this way is quite difficult. Okay, so for that, what we need to do is the following. Mm, So, so for that, what we need to do is the following. So, okay, sorry. So it seems quite difficult directly, but without using anything extra. So those who have, so the same thing here. For this also, we need to use some tools in algebra topology, name as homotopy, homology. Okay, only using those things, this problem can only be solved. Otherwise, not. Okay. So for the timing, let's skip the problem here because it is not beyond our scope. Okay. Now, okay. So now now let's there's an interesting problem. Problem is that let X be a compact metric space. Show that. every sequence x in X has conversions. So this is what, suppose X is a compact matrix, so that every sequence X in X has a convergent subsequence. How to show that? So of course, now okay, so this type of problem can come in the exam also. That's why it's important to solve this type of problem. Okay. Hmm. So how to do? Okay. So mm, so for doing this step one one right. So think about I should get about 2 minutes. Hello, yes, sir. Hello. Hello, am I audible? Hello, am I audible? Okay, there is some, sorry for the inconvenience. Okay, so, okay, so now so, so, okay, so the question which we are solving is the following. Okay, okay, so what is the question? Suppose, okay, so before starting, Musta, can you please let me know whether I'm audible clearly or not? And the screen is visible to you because it seems there is some internet issue. Can you please confirm, sir, whether I'm audible and the screen is visible to you or not? Mustaq, can you please confirm whether I'm audible and the screen is visible to you or not? Okay, I hope the screen is visible to you. One- Well, so now let's get to this problem. So how to solve? Suppose, okay, so we need to show that X it has a convergence of sequence. Okay, so how to do that? Okay, so uh, the process will be as follows. Let Xn is a sequence with convergent subsequence. Okay. Then every x belongs to x, there exists Rx greater than 0 such that Brx it has only finitely many terms in common with the set of xn n belongs to n. Okay, correct. So with the set xn n belongs to n. Okay. Now since um this set Brx x belongs to x forms an open cover for x, so the compactness of x gives us a finite subcover BR x1 BR in xn, right? But observe that each BR xi contains finitely many elements. Okay, from the set xn n belongs to n. So we see that the set xn from n belongs to n itself is finite. But then there exists, but then there exists a term xj of the subsequence xn such that xj is equal to xn. Okay. Okay, for infralimitian, thus x is has a convergent subsequence, namely the constant sequence, okay, of terms equal to x. This contradiction proves that xn must have a convergent subsequence. Okay, so this is the argument. So this is the argument. Okay, so go through this and let me know. Okay, so before going further, let me re-describe this argument. So what do we need to show? We need to show suppose x is a sequence with convergent, then we need to show that every sequence has a convergent subsequence. Okay. So okay, so hmm. So that if for every x belongs to there is a r is greater than 0, so b r x n comma x has only finitely many terms in with at least two set xn. Now since b r x forms an open cover for x, so compactness of x give a give a finite subcore of b r x n. First subcore of b r x n. Okay. Now, from the set xn, we see that the set xn from x, x itself is finite, but then there exists a term xj of the subsequence xn sub xj is equal to xn for infinitely many n. Okay, this xn has a convergent subsequence, namely the constant sequence, whose terms are equal to j. And this is the contradiction of the fact that xn must have a convergent subsequence. So this is the argument. Okay. So till now, let me know, do you have any question or confusion, or else we shall go for the next question. Do you know till now? Till now, let me know. Do you have any question or any confusion or doubt? Okay. So then let's go for the next problem. Show that every compact metric space is complete. That is, every compact metric with every Gaussian converges obstacle is what to show. Think about it. This is a question comes directly on definition. Think about R. And in the meantime, let me find out some good problems. Okay. So okay. So you need to show that we see that is what you need to show that is to show every Cauchy sequence is convergent. There is every Cauchy sequence is convergent. This is what need to be shown. Think about it. I'll get back to it. Well, so it was work fine. Hmm. Well, so how to what to show actually? So that every compact metric is a complete. Okay. So this is every consequence convert. This is what I need to show. Okay. Show how to show. So, so I mean, so look, I mean, it's not difficult. This can be this so problem can be solved in many ways. Okay. So here I'm describing one way of solving this problem. Okay. So, hmm. So every Cauchy converse is what need to show. Okay. So now we know that. I mean, suppose if a Cauchy sequence has convergent subsequence, then the sequence itself is convergent, right? Then the sequence itself is convergent. And also note that, so note that every sequence in a compact metric space has a convergent subsequence. So thus, thus, if X is a compact metric space and if Xn is a Cauchy sequence in it, then Xn has a convergent subsequence. Thus, if X is a compact metric space and if Xn is a Cauchy sequence, Xn is a Cauchy sequence, and Xn is a Cauchy sequence, then Xn is a convergent subsequence. Hence, Xn is convergent in X. This tells X is complete. So this is the argument. So uh, so this is the first part of the argument. Please let me know if you have any doubt and question the first part of the argument. Then we shall go to the second part. I shall give uh, think about it, or else let's go for the second part of the problem. Okay, so this tells that X is complete. Okay, so for the second part, what we can go is the following. For the second part, mm, so since R with discrete metric, since R with discrete metric not compact, so that's the open cover P1x, X belongs to R, does not admit finite subcover. However, this space is not complete. However, this space is not complete. Why? Because every Cauchy sequence in it is an eventually constant sequence and hence convergent. Okay, so these are good. So now let's repeat the argument. So what we need to prove that every Cauchy convergent, okay? So if this is the case, this implies what? The sequence itself is convergent. And note that every sequence is a compact metric has a convergence of sequence. Thus, if X is a compact metric space and if X is a Cauchy sequence in it, X is a convergence of sequence. This if X is a compact metric, X is a convergence of sequence. So this tells X is complete. Okay, for second part is quite easy. Okay, so now okay, so now let's mm, okay, so now let's try to solve a question. Uh, so think about how to show S1 cross S1 and S1 cross I are not homeomorphic. Think about it. This is S1 cross S1. Okay, this is S1 cross S1, and these are S1 cross I. This is S1 cross S1. This is S1 cross. So I need to show that these two are not homeomorphic. Okay, how to show this? Think about it. I mean, of course, from picture it's clear it's not homeomorphic, but in order to show it's quite difficult. Yeah, this one is not home. Okay, so okay, so think about it somehow you can try to go with the method of removing or putting some extra point. So think about it and let me know how we can solve this problem. Okay, so that's all for today's session. We shall meet tomorrow from 5 to 6. Okay, so let's end here. If you have any doubt or any question, you can ask me in the next. You can ask me in the tomorrow. Remember that tomorrow is the last live session for this course. Okay, so try to utilize the last session as much as you can. So thank you for attending the session. I'm leaving the session right now. We shall meet tomorrow, Saturday, from 5 to 6.